I will start. So we were talking about some things, and I will go over them. Did you zoom to this board, or? No, I'll get it. Oh, she's got it. So Bethany asked me to just basically look at some examples, and I thought, okay, just revisiting this one, if we take z2x mod x squared plus x plus 1, we haven't done anything yet, Emily, don't worry. We're just looking at some examples. So I wanted to re-examine that example in the light of the theorems that we have just now discovered in lectures 29 and 30. And so I started by showing that if we look at f of x equals x squared plus x plus 1, that if we plug in 0 or if we plug in 1, we get non-zero, which then says that f of x has no 0 in z2, which means it's irreducible since it's quadratic with no zeros. Therefore, this E, built by that quotient, is a field, because it's a quotient by a maximal ideal, right? And more than that, the theorem that I did at the end of today says that, in fact, E is a two-dimensional vector space over Z2. And the basis is 1 in alpha, with alpha defined as usual as x plus the ideal generated by the irreducible. Now, that's not to say that there are two things in here, right? If it's a two-dimensional vector space over Z2, it's got 4 things in it. All right. So then I was asking the question, like, what if we expand our inquiry about factor rings a little bit more, and we're not, like, we've been very focused on field extensions in lecture recently. Maybe focused is the wrong word for me, but all right. What if you don't quotient by an irreducible? What if you quotient by something that's not a maximal ideal? What does that look like? Can we say anything about those kinds of things? And I think that really it's still the case, the basis theorem actually still makes sense. If you look at the argument I gave today in terms of proving that 1 through alpha to the n minus 1 is a basis if you quotient by a degree n polynomial, it has nothing to do with, really with the irreducibility of the polynomial. What I mean by that is the dimensionality, the linear independence of 1 alpha, alpha squared, alpha n minus 1, that did not use the irreducibility of the polynomial whatsoever. The reason we needed the irreducible, I'll put it back up and talk about it again, you guys know what I'm talking about. The reason we needed irreducibility of the p of x in that theorem at the end of class today was to prove that this was a field. It's still the case, though, that if you take and divide by, if g of x is equal to a0 plus a1x plus plus anx to the n, where an is not equal to 0, what I'm arguing, guys, is that f of x is that the field, polynomials in the field, mod the principal ideal generated by g of x, that's still the span over the field of 1 alpha, alpha squared, alpha to the n minus 1. That is a theorem which does not require the irreducibility of g of x. Why we needed irreducibility of g of x was to make that a field. If we're just interested in studying it as a ring, we can still say, you know what? It's a vector space of dimension n over the base field. And so an example of that in the finite case we were looking at before I turned the camera on, because Bethany wanted a finite example, and I respect that. So this here is just a side comment, like for this example. For this example over here, I was like, so if you think about the representative, we can still do the, even though this x squared minus 1 is not irreducible, because it has zeros, 1 and minus 1, you can still look at the division algorithm and see that any representative in this quotient ring can be reduced to just a linear representative. And as such, really, you have things of the form a plus b alpha, where alpha is x plus the x squared minus 1. So again, this is going to my point, is the fact that it works out like that has nothing to do directly with the irreducibility. The fact that we want irreducibility is because we want the quotient to be a field. If we're not interested in that, we can still say things. They're just uglier things. Yeah.
Can you say one more time about the two-dimensional, how you get the four things? And like,
Oh, sure. It's because we figured out that this is an arbitrary element in E. And so A and B both take on values in Z2. And the 1 and the alpha are independent. That means that you can't write this as a linear, these are not the same element in disguise or something. They're linearly independent. So
in relation to the base, so like if there were three things in that basis,
then
it would be 6.
Indeed. Oh, yeah, sure. If we were to look at, say, Z3 x mod x cubed, that would be three-dimensional over Z2. It would also not be a field. What would that be? It would be three-dimensional over Z3. It would have 27 things in it. What would it look like? You could write this as like A plus B alpha plus C alpha squared, such that A, B, C are in Z3. And what the rule would be is alpha is equal to x plus this, right? And you work out the rule that x alpha cubed is 0. So that would be the calculational guide in that factor ring. Alpha cubed would be 0. So yeah, we're just looking at some examples of factor rings which are not fields. Yeah? So let me get back to elaborating on the example we already talked about, Bethany. So Z3 mod x squared minus 1. We know x squared minus 1 factors, right? Which goes to show you that the product of these two things in the factor ring, which I'll rewrite as x plus 1 bar times x minus 1 bar, well, that's equal to x squared minus 1 bar, which is, by the way, 0 bar because x squared minus 1 is in the ideal I. So what this shows is essentially that, I mean, you could write it this way, x bar squared is equal to 1 bar, right? But if you don't want to put bars on things, we just introduce the alpha, and we write things like alpha squared equals to 1. It's an abusive notation, but I hope it's one that you'll allow me. So essentially, this factor ring is A plus B alpha with the rule alpha squared is equal to 1. It is not a field. It has 0 divisors. For example, alpha plus 1 and alpha minus 1 are 0 divisors, right? So like alpha plus 1 times alpha minus 1 equals to alpha squared minus 1, which is equal to 0. So those are two non-zero elements of this factor ring whose product is 0. It's not an integral domain, which goes to show you that the principal ideal generated by x squared minus 1 is what? It's not prime, right? It's not a prime ideal because it led to a quotient, which was not an integral domain. Okay, so I think that pretty much expands on the examples that you asked me for before class. So I'll transition to talking about.
What is the difference between the brackets and the parentheses?
Okay, so what's the difference between brackets and parentheses is the question. See, I see it over there, but not over here. It's weird. Oh, now it's here. Difference between brackets and parentheses is that the... I need to... Sometimes there's no difference because they happen to be the same thing. Oh, sorry, Emily. Have I...
No, I already had that fight.
You good? Okay, okay, all right.
If the math department is closed, would you be able to get us in? So that we can
Oh, yeah.
go out?
Are you going to vandalize Dr. Sprano's office or something?
Absolutely.
Okay, then I'll let you in.
I'm going to organize it because I think that would
You're gonna, you know, that is true. If you went in and organized it in his absence, he would be outraged. If in some point, you're not married right now, right? Okay, just checking. So, if you do get married at some point in the future, and you want to make your husband really, really angry, just go organize his stuff without before talking about it. Just like nag him once, and then just go organize it. See how it helps your relationship. That has never happened to me, actually. I just know how these things are. Okay, so I was getting to a point. There was a point I was going to make. Oh, brackets versus parentheses. All right. So this would be is like the contrast of white on white. So this is, what this would be is the ring with the square root of 2 adjoined. This would be the field with the square root of 2 adjoined. But the thing is, we have proved that if you adjoin the square root of 2, you automatically get a field, so these are equal. It's more exciting if you look at something like this. This is the reals with x adjoined. X being indeterminate, we recognize these as polynomials. On the other hand, if you have R like this, that's the field which contains the reals and an indeterminate x. So what's that? It also happens to be the field of fractions for polynomials. That field of fractions thing we did, remember? We took any integral domain and built a field of fractions over the ring. They're not equal. No, this is things of the form f of x over g of x, understanding that that's a sophisticated notation for an equivalence class, mod the cross multiplication similarity relation, the equivalence relation that was based on a formal mockery of fractions, if you will. It's an explicit construction that builds fractions for any ring. You can do it for polynomials. And so there you go, such that f of x, g of x. Of course, you maybe recognize what this is. What are these? These are, you know, up to an evaluation homomorphism rational functions. I would say that they're rational indeterminates or something, maybe, to be more, because we're not thinking of f of x and g of x as functions here, but using, if I say that f of x is a polynomial function, then by the same abuse, I may say that f of x over g of x is a polynomial function.
Why do you say that to, whatever the word you said, up to the evaluation homomorphism, why did you say that as rationals rather than reals?
Those are rational functions. Like, that's not about rational numbers. The quotient of polynomials, rational functions.
This is like the key with brackets over there with an x instead of over 2.
Up here?
Sorry.
These are
Q
ra-
over here would be equal to Q bracket X.
No, we don't. That's not notation that we use. No.
Wait, wouldn't that be polynomial with coefficients from?
But these aren't on.
Oh,
These are
well, we could
coefficients.
we could talk about this. Sure. Then that would be. I mean, I'm not saying you're wrong in terms of it being a thing. It's just not the thing I think you were saying it was. I could be wrong. I could have misinterpreted you. It's certainly within my power. Like, this would be Q parentheses X. This is rational polynomial, rational functions built from rational quotients of rational polynomials.
But Q bracket X would be
That would be
polynomials with rational coefficients.
correct.
Now I got Q.
So this would not be this, no.
So what's the
Because
one right above it?
this could have something like 1/3 x squared plus 7 divided by x to the 19th plus 20. And that would not be an element of this. The numerator and the denominator of the thing on the right are both in Q square bracket x. So as a general rule, square bracket x is a ring, but parentheses gives us a field. But, you know, sometimes if you just adjoin an element to a field, it's automatically a new field. What I'm trying to say is, you actually work, this is a homework problem for you guys. You have shown that if you adjoin square root of 2 to q, in other words, if you look at things of the form a plus b root 2, that has a multiplicative inverse in terms of things of that type again. What's the multiplicative inverse? It's a minus b root 2 divided by, how's it go? A curses. Remembered eventually. So this equals 1. But this works out to a over a squared minus 2b squared plus, well, rather minus b over a squared minus 2b squared square root of 2, right? So this is an element of Q bracket square root of 2 because it's of that form. So that's the funny thing, is when you adjoin the square root of 2 to the rationals, it's already a field.
Okay, so when parentheses are involved, is it always a field of fractions?
Is it always a field of fractions?
So like Q squared root of 2, the square root of 2 adjoined, that's a field. Is that...
I mean, you could think of it. I don't think of it that way. I honestly, I don't think of it that way. I just think of it as a larger field which also contains that. But you're right. I mean, I could think of that in terms of always going through the field of fractions construction, sure. But I stated a definition at the end of 29 where I said that f adjoin alpha 1, alpha 2, alpha n. It's the smallest field, smallest extension field of f, which contains alpha 1 through alpha n. Right?
Is what?
F alpha 1, alpha 2, alpha n is the smallest extension of f containing alpha 1, alpha 2, alpha n. Now, is that a field of fractions over f? I don't know. Not necessarily. I mean, if I'm working with reals and adjoining like a complex number, I can just think of it as the complexes. Do you think the complexes are a field of fractions over the reals? I don't know. I don't think of it that way. It could be, here's a stupid case. If alpha 1 through alpha n are all in the field F, you know what this is? It's just F again, right? If alpha is an element of F, then F adjoint alpha is just equal to F, because that's the smallest field which contains both F, the things in F and alpha. This is the notation.
Okay. But then, so for R parentheses X and Q parentheses X, the reason that you define them that way is that that's just how they are defined specifically for them. They happen to be a field of fractions. But that's not always the case. That just is the case.
Well, I don't think R of X is a field of fractions, but you're saying that one is a field of fractions.
R parentheses X and Q parentheses X. You define them both as polynomials.
Right. Well, I mean, we're starting to run into sort of philosophical questions, like what are the complex numbers? Are they 2 by 2 matrices of a certain type? Are they equivalence classes of? Excuse me. Are they points in the plane subject to a certain multiplication? What are they? So like.
So is that just a way that you chose to
Certainly,
demonstrate them?
Certainly, I can. Yes.
Okay.
I mean, certainly, I can say that a field. What's the inverse of X in R adjoint X? What's the inverse of X in here? X times what equals to 1 in here? What? Mm-hmm. Yeah, I mean, like, what f of x and what g of x makes this be 1? Uh-huh. Yes.
Okay.
But that's a radically different object than polynomials, right? Like, quotients of polynomials versus polynomials, these are different things. So rational functions form, and I shouldn't say functions, like that bothers me to say that, but I don't have another word.
So, is the one with the brackets always a subset of the one with the parentheses?
I think that's fair to say. Yeah, I think the one with brackets is a subset of the one with parentheses. I feel like I'm being lawyered into something. I can't shake the feeling like this is all leading up to, well, then you killed your own mother or something. I don't know. It's like the mathematical equivalent.
I was just wanting to make sure. I was just wondering what the significance was. I think we kept on asking questions, and then you would answer those questions in a way that would make us have more questions. And so we were trying to kind of trace the tree back to the beginning.
Okay,
where
okay.
we made sure that we knew why you did everything that you did.
Very good. Let me share with you the essential features of lecture 30 so that we may proceed calmly next week. You have a test, right?
Yeah, it's supposed to be on Wednesday.
Oh, yeah.
I gave a mission due Monday that we will need the solution for to study for Wednesday.
But I thought that somebody told me that mission was due next Wednesday.
No, it's due Monday.
Oh.
Because we needed to study for Wednesday.
Oh.
So we will need a solution just to have
Oh, okay. Well, I've solved most of the problems for various people in here at this point, so.
Preferably before Tuesday night.
For example, I can tell you that after you sort through the details, I think you'll find 8 cosets in the Gaussian integer 1. I know because I've drawn the picture for like 3 different people now. Let's see here. Yeah.
That's a lot of people in the class who are on top of things.
That is true. Those are people who will pass. Let's see here. Yeah. Look what you've done to me. You've ruined my lecture. Look, my lecture's hideous. All right.
Oh, Eisenstein's does work for 29B.
It does?
Yeah.
Oh, man. 69B?
Yeah, 69.
Well, that's so disappointing. I wanted Eisenstein to fail, so you guys had to actually, like, think about it.
It worked.
Oh, man. See, because when I chose a couple of different other primes, like 5 and 7, and found the polynomial which is...
It actually works in the case of 2 and 3.
Dang it. So I was nice to you guys, is what you're telling me. I didn't even mean to be nice. Dang it. All right. Definition. An extension E over F is algebraic. All right, so the picture, like that again, right? If every element of E is algebraic over F. All right. If E is not algebraic, then it's said to be a transcendental extension of F. All right. Before I, whoa, goodness gracious, another definition here. If an extension field E over F forms an n-dimensional vector space, all right, n-dimensional vector space over F, then we say E is a finite extension of degree n squared. No, I'm just messing with you. Degree n. Degree n. And right. And so here is some notation you've seen before, but now it has been repurposed to mean the dimension of E over F. Before I even, yeah? Go, yeah, go ahead.
I was going to say that makes sense because before it was like it was G over H.
Right.
So it makes sense because it's like E over F.
Yeah, right. It's very much parallel to the story of Lagrange's theorem and subgroups and finite counting, but here we're talking about dimensionality of vector spaces, which is a different kind of counting, right? Which works for infinitely many things, because we still have this finite basis. So some examples before I go to the theorem. Let's just an example or two. Certainly, if we look at Q, I join the square root of 2 over Q. That is an algebraic extension, right, of degree 2. Why, how do I know every element of Q adjoin alpha, Q adjoin square root of 2 is algebraic? Good grief. Morons. Well, any rational number is algebraic over Q, right? Because x minus that rational number is its irreducible. And why is the square root of 2 algebraic over q? Because it is the 0 of x squared minus 2, which we've discussed today is irreducible, right? So every kind of number in here is algebraic. You're like, so you're saying the linear combination of algebraic numbers is again algebraic? Yeah, this you can prove. That seems like a question for next semester, though. Anyway, my point is you can argue that in fact it's an algebraic. We'll soon find a much easier way of proving it's algebraic, okay? So don't fuss too much. On the other hand, if we look at the reals as an extension of the rationals, this is a transcendental. Why? Pi and e not algebraic, right? There's no polynomial for which pi or e, rational polynomial, for which pi or e appear as zeros. I'm claiming that, I'm not proving it, right? So that makes the reals a transcendental extension of the rationals. Which means, by the way, that it's infinite dimensional as a vector space over Q. Although that's not clear, perhaps, until we prove the next theorem. So here's the theorem, which will clear everything up, I think. A finite extension field E over F is an algebraic extension. A finite extension field E over F is an algebraic extension. The proof is suspiciously short. Let's see if we can understand it. All right. So I say let alpha be an element of E where the dimension of E over F is equal to n. What's the question? Oh, okay. Like, it's not always about you. Fine. I'll accept it.
We were talking about game night.
Talking about game night? Pancakes? You know, I used to make pancakes in my office.
Really?
Yeah. Nothing brings Russians like pancakes.
The day that we have ice cream and complex, we could make pancakes in abstract.
The day that we have ice cream in complex, we can make pancakes in abstract. That seems very logical to me. Although I would worry that you're anchoring the existence of pancakes in abstract on the existence of ice cream in complex. You might want to disconnect these events to make both of them more likely, because when you take two unlikely events and you put them in sequence, if you know the laws of probability, as many of you are well versed in because you study for exams. But let's see here.
But you can't try the whipped cream unless we have ice cream.
And we could, if we had enough of that whipped cream, we could also try it on the pancakes.
Exactly.
I see where you're going with this.
Yeah, why not?
Pancakes with ice cream. Ooh. All right, this is not getting this lecture done. All right, so if we have a finite extension field E over F is an algebraic extension, great. So pick alpha in E. It's got finite dimension, right? And then, so check it out. You tell me what you can tell me about this. 1 alpha, alpha squared, alpha cubed, alpha to the 4th, alpha to the n is a set in E with blank vectors. Count them. N plus 1. So then what? You're like, I took linear algebra already. I refuse to learn anything from linear algebra and extract it and apply it in this course. It worries me greatly. You're talking about words like linear independence and basis right now. You're violating my safe space. Mathematically speaking, you need to stop. And your mind space. I was earlier questioning what would a liberty space be? Like, how would you define the liberty space? Like, what would that be? You live in liberty space? A liberty bubble? Oh, but anyway, n plus 1 vectors, which says what about that set? In an n, it's what? Not independent, which we could also rephrase as being dependent. So that means that there exists C0, C1, Cn in F, not all 0, such that what? C0 plus C1 alpha plus C2 alpha squared, plus Cn alpha to the n equal to 0. Wow, look at that. So we let f of x equal to C0 plus C1x plus C2x squared plus plus Cnx to the n, and observe that f of alpha equals to 0. So apparently alpha is algebraic, right? See, either that's the irreducible polynomial for alpha, or the irreducible polynomial for alpha divides that. You know, actually doesn't concern us. If you can find a polynomial which sends it to 0, it follows that by definition the element is algebraic, right? It may or may not be the case that f of x is actually its irreducible polynomial. Who cares? Which alpha are algebraic? Oh, arbitrary alpha, right? Which is what we need to show that f is an algebraic, that E is an algebraic extension of F. Yeah. And we proved that earlier one. In class, I proved that if we had a transcendental element, then we had a we had an injection of polynomials in the element, right, as a subset of the extension field. We argued that the kernel of that thing was 0. So essentially, if we're taking a field and we're adjoining a transcendental element, it's necessarily infinite dimensional. Yeah? Because polynomials, what's the dimension of polynomials over the reals, for example? What's the basis for the polynomials? The monomials, right? How many of them are there? 1, x, x squared, x cubed, x to the 4th, x to the 5th, to the 7th. Oh, I forgot the 6th. Oops. Anyway, you get the idea. Okay, so how do I know then, again, so going back, I now have a way of proving, right? Yep.
Did you say if you join a transcendental element, then
Because that's not at odds with the definition that's here. If I have a transcendental, if I've adjoined a transcendental element, that means that element's not algebraic. So that means that there exists an element in the extension which is not algebraic, which is to say it's not an algebraic extension.
and it has infinite dimension
Over the base field, yeah. There's more here, though. There's more here. We're on the cusp of seeing something. So notice that P of x divides f of x, where p of x is equal to the irreducible polynomial of alpha over the base field f. So what does that say? What does that say about the possible degrees of elements in the extension f? Yes.
Is this like a new thing, or is it a continuation of proof?
It is me extracting another pound of flesh from the proof.
But we have proven this already?
It's proved.
Just for the sake
Proved.
Just for the sake of it.
Proved. Yes. You can put one of these deals here, and then partition off this me jibber jabbering down here as a separate comment. But we had that theorem today that I didn't prove, that I skipped over, where I argued that the irreducible polynomial must divide any polynomial which sends the element to 0. So if I have a quartic over my base field, which the evaluation homomorphism for the extension sends to 0, it may be that element has degree 4, or it may be that it has degree 2, because there could be a quadratic factor in the quartic which makes it 0, right? Or stupider still, it could actually be in the base field and have degree 1. So look at it. What's the rule here? The degree of p of x must do what? Yeah, I think the degree of p of x has to divide the degree of the f of x, right? But this f of x is not based on what? This is not based on the particulars of the element. This is based on the degree of the extension. So what I'm trying to say is if I have a degree 4 extension, if I look at numbers inside that, the numbers, I think, unless I'm missing something, the numbers must have degree 1, 2, or 4. So you can't have like a degree 3 number inside a degree 4 extension of the rationals, if we're working with the rationals or something like that. That's actually kind of, I just feel like that could be useful for something. I don't know. I don't think I've assigned you any homework on that or anything. It's just something I'm seeing at the moment. I thought I should share with you. Yeah.
Can you just say again what that notation is with the IR?
This is the irreducible polynomial of alpha. This is the polynomial of least, what this means is that p of x is monic, and p of alpha is equal to 0, and it's p of x least degree. For which that happens. It's the polynomial of least degree which sends my element to 0. So to give a stupid example again, if we pick c in the field, then x minus c, if I look at that p of x is equal to x minus c, has p of c equal to c minus c equals to 0, right? So the irreducible polynomial of c over the field is just x minus c, for the stupidest example. Much more interesting, like if we look at the irreducible polynomial of I over the reals, what's that?
X squared.
Yeah, x squared plus 1. On the flip side of things, if I did irreducible polynomial of I over c, what would it be?
X minus I.
Mm-hmm. If I did the irreducible polynomial of I over q adjoin the square root of 2. Brackets or parentheses, your choice. Oh, it's always possible. We've proved that it always exists. Yes. Kroneker's theorem that says there always exists an extension field in which we can make the element be 0, yeah? What's that? I mean, there always exists, well, I don't, maybe I said that the wrong way, but what is that? Anyway, I'm misstating Kroneker's theorem at the moment, but set that aside. Yeah, it's still x squared plus 1. Because I is not in Q adjoining the square root of 2. Right? Same. So like, all right. One of my absolute favorite theorems in this entire course is the one I'm about to show you. If I have time, it's debatable. Yeah, I think we're okay.
Can I ask another question?
Yeah, you go for it.
I feel like you probably answered before. What does monic mean?
Monic means that the leading coefficient is 1. So I want to prove this theorem 4.10.4, which I'll put up on the board here.
There's always an extension field where anything has 0 or
If I, let's see, if I take a polynomial, the proper statement is this: if I have a polynomial over a field, right, there always is an extension field in which that polynomial has a 0. And if you just keep applying that successively, that means that you can always find a large enough extension field to, kind of break any polynomial down into linear factors. So this is, if we have, try to draw some pictures here. We want E over F and K over, let me see here. I think my wording is wrong. I want K over E and E over F. So K is at the top. So F is my base field. E is my intermediate field. All right? So we're looking at an extension of an extension. All right? Then the theorem, I'm not sure my wording is right. E is an extension field F, yeah. That's supposed to be K is an extension of E. K is an extension field of E. Yeah, E. So my what's that? There's a typo.
Yeah, what is it supposed to be? That's the only part that's wrong.
Right on the second, right after the, goes to the next line, K is a finite extension field of a field, not F, but E.
There were too many letters. But
Yeah.
the result is still true after that.
Oh yeah, that's fine. So let's, for the sake of discussion, suppose that, the degree of E over F is n, and let's suppose that the degree of K over E is, I'll use a P, so you can, tempted to use M, because I'm going to use M. Feel better about it now. So what that means, first of all, is the extension of an extension an extension. So what does it take to be an extension field? Why is K an extension over F? It's very simple. It's since E extends F, that means F is a subset of E, right? And since K is an extension field, well, F is a subset of E, and since K is an extension of E, thus E is a subset of K, So you put this and that together, what do you got? F is a subset of E is a subset of K, right? So F is a subset of K, which is all I need for K to be an extension field, is that the given field, the given base field appears as a subset of the larger field, and they share the same set of operations. So it is an extension field, right? So therefore, this, we can calculate the degree of K over F. Makes sense to calculate. All right. So, great. The rest of this is linear algebra, which of course makes me happy. Now, so what does it mean to say that the degree of E over F is what? Is n? So number one, the degree of E over F being n means that E is equal to the span over F of, let's say, well, E1, E2, what? En, right? Where we could say that this is, let's call this beta, beta sub E for lack of imagination, is linearly independent over F, right? It's a basis. Likewise, 2, we know that that K has dimension m, as in mummy, over E, which implies that K is what? It's the span over E, the E span, of, let's say, K1, K2, Km. And this beta sub K is linearly independent over what? Over E. So what do you guys think the basis? So the thing is, we can build a basis for K over F as follows. So we'll let beta, well, I just give it a new name altogether. I'll call it gamma, which is going to be simply formed by EI Kj, such that 1 less than or equal to I less than or equal to n, 1 less than or equal to j less than or equal to m. My claim is that this set gamma forms a basis. My claim is that this is an F basis for K. So to show that that's actually a basis, what do we need to do? Show it's linearly independent and spans, right? So let's start out with spanning. I think that'll actually give us the linear independence just the same. So let's let x be an element of K. Then we can write x as equal to what? The sum over xi, k, I'm going to say xj, kj, j equals 1 to m, right? Why can I do that? Because the k1 through km forms a basis for k. And what are my x's? They're elements of E, right? But then what can we do with the x's? X sub j is an element of E, therefore what? It can be written as a sum, I equals 1 to n, of, let's say, y, ij, ei. Why can I do that? Because if xj is in E, it can be built from a span of the E1 through En. where the coefficients y sub ij are where? They're in F, right? Put it all together, what do you got? X is equal to the sum I equals 1 to n, sum j equals 1 to m of y I j ei times kj, which of course is an element of the span of gamma with f coefficients as advertised. Therefore, gamma is a spanning set. This argument's very straightforward, really. There's nothing very sophisticated about what I'm doing at all. Then, to prove linear independence, what do? Set it equal to 0, right? If you set this equal to 0, then you can argue that by the linear independence of the beta k basis, that these must be 0 for each j, right? So you get that the linear combination over I can flip these sums, or let me not write anymore. I'm just going to talk. I can flip the sums, and I can look at this as the sum j equals 1 to m of linear combinations of yij ei. Each one of those linear combinations must be 0 by linear independence of the k1, k2, km. But then you apply linear independence of the beta e basis to get that each of the yij's are 0. So it's a combination of linear independence of each basis, one after the other, and that gives us, of course, linear independence of gamma, which proves that gamma is a basis. How many things are in gamma? Counting, right? Mn. So there you go. The number of things in gamma is the dimension of k over f, and we've just proved that that's equal to m, which, by the way, is k over e, times n, which is, by the way, e over f, and there you go. This also puts very strict limits on how you can look at like an extension as an extension of extensions, right? Like if I've got an extension 4 over a base field, I could perhaps see that as a quadratic extension of a quadratic extension. But I couldn't have like a degree 3 extension if my total extending degree is 4, right? See, the degree of an extension, the degree of an intermediate extension has to divide the degree of the total extension. The degree of e over f must divide the degree of k over f. It's obvious from this boxed formula. So, I have the gory details in the notes, of course. They might even be right. See what I'm doing here? This is that linear independence calculation I was just talking through. I said set that equal to 0, factor out the beta j, which is the notation I used for the upper basis, and then linear independence of the beta basis gives me that these have to be 0 for each j, which gives me that. But then linear independence of the alpha basis tells me that each one of these must be separately 0. So in total, we have that all of the coefficients of the linear combination are 0, hence linear independent. All right. And you can do this more than once. You could just, if you can do it once, you can do it again. And so if you have an extension of an extension, you got, composite extension formula. And again, this is what I was trying to say a bit ago, was if E is an extension field of F and alpha is algebraic over F and beta,